Hi, I'm Cassie, and I'm going to walk you through question 25 of the AAMC's official physics question pack. So this question is still related to passage 4, which is all about our photodiode detector and the photoelectric effect. I love this question because it might seem pretty straightforward, but it gets at a lot of really important electricity-related concepts for the MCAT, including potential energy, kinetic energy, conservation of energy, and the photoelectric effect. So let's break this down. First of all, let's start off with just understanding what we've got going on. So all of this is happening inside of a vacuum, but essentially we have a cathode, and then of course we have another electrode, that's our anode, over here. And what are we doing? Well, we're taking a light, and light has photons, right? So we're taking a light and shining it at our cathode. Our cathode is made of metal, and then what's happening is we're ejecting electrons off of our cathode. So this is what we call the photoelectric effect. The idea is that metals, they're known for having electrons in their outer shells that aren't held very tightly by the atoms. So we call these sort of free electrons that can just kind of move around in the outer parts of those metal atoms. And because those electrons are not bound as tightly, it's easier for them to jump off of that metal. And how does that happen? Well, one way we can make that happen is we take a light and we shine it at the metal, and then light, photons, right, are energy. And so some of the atoms of that metal are going to absorb the energy from that light hitting it. And then those electrons, if they absorb enough energy, they're going to get kicked out of that metal, or we say sometimes ejected from that metal. So how much energy do you need for that to happen? Well, it depends on the metal. Every metal, part of its properties is how much energy it needs to absorb to eject those free electrons. We call that the work function of the metal. And like I said, it's different for every different type of metal. So what happens once that electron has been kicked off of the metal? Well, any energy that electron has left over above and beyond whatever the work function for that particular metal was gets turned into kinetic energy that then is going to propel the electron forward. So we can also represent this in equation form, and this is an important equation to know for the MCAT. The kinetic energy of an electron that gets ejected from a metal is equal to HF, and we know that equation. What is HF? HF is the energy of a photon, right? So it's equal to the energy of a photon minus the work function for a metal. And so you'd be usually given that work function in an MCAT problem where you had to plug into this equation. So just to give an example, like let's say the energy of our photon, we calculate that, we take H, which is Planck's constant, and times it by the frequency of the light, and we get 5 eV, electron volts. And then we're told that the work function of our metal is 4 eV. Well, then we'd still have 1 eV left over to turn into kinetic energy that's going to accelerate that electron forward. So we're told in the passage that when the electron gets ejected from the metal, it only has just a little more energy than the work function of the metal. So if I was going to graph the amount of kinetic energy and the amount of potential energy our electron has over time, let's do kinetic energy in yellow because I feel like kinetic energy, movement, excitement. So when we start out, we're going to have very little, I'm going to label this KE, kinetic energy. But what about potential energy when we start out? Well, we know that electron is released into an electric field. We're told we have a 50 volt electric potential difference between our cathode and our anode. And our cathode, it says, is connected to the negative terminal of the battery, so it's going to be negatively charged, versus our anode, which is connected to the positive terminal of the battery, so it's going to be positively charged. So our electron, of course, being negatively charged, and our cathode being negatively charged, we're going to get a lot of repulsion there when that electron is first rejected. And when we have repulsion, we've got instability. So that's going to be a lot of potential energy that we have at the beginning. So whereas our kinetic energy to start is very low, our potential energy, we'll do in green here, is very high. Remember that you should know the equation for potential energy of a particle for the MCAT, and you've got potential energy is equal to charge times voltage. So we know that the charge of an electron is equal to negative 1.6 times 10 to the negative 19th coulomb. But that'll usually be given to you if you need it for a problem. The important part is just to understand what that Q represents, that it represents charge, which is negative in this case because we're talking about electrodes. And then our voltage here, well, we're told that we have a 50 volt electric field. So when our electron is first ejected from that cathode, its potential energy, QV, is going to be essentially Q times negative 50 volts, because the potential of the cathode relative to the anode is going to be negative 50 volts. But then as we move towards the anode, what's going to happen? Well, our potential voltage difference decreases. So be in the middle part here, instead of at being negative 50 Q, here we're more at like negative 25 Q, negative 10 Q, etc. So what's happening as the electrode goes from the cathode to anode is that our potential energy is actually decreasing. So I'm going to show that on our little graph here. Basically, our potential energy is decreasing down. And what do we know according to the law of conservation of energy? Well, we know according to this law that our change in kinetic energy plus our change in potential energy must be zero. In other words, if we increase the amount of kinetic energy, we must decrease the amount of potential energy, or if we increase the amount of potential energy, we must decrease the amount of kinetic energy. And that's exactly what's happening in this problem. So that tells us that just according to that principle, we know that if our potential energy is decreasing as we get closer to the anode, then our kinetic energy must increase as we get closer to the anode. But let's make sure we understand why that kinetic energy is increasing too. Remember that our equation for kinetic energy you should know for the MCAT is kinetic energy is equal to 1/2 of the mass of an object or particle times its velocity squared. So in terms of why our kinetic energy increases as we move from cathode to anode, well, do we think the mass of our electron is changing? No, that's just like a stable property, right? So that always stays the same. So what must be increasing is our velocity is increasing. And why is the velocity of our particle increasing? Well, remember that electric field is just a region where if you place a charged particle in it, that particle is going to experience a force. And the force on that particle you place in an electric field, in this case we're talking about an electron placed in an electric field, is going to be given by the equation F equals QE. Remember, just like in our potential energy equation, that Q is going to be the charge of our particle, and we know our capital E is going to be the electric field. So in this case, as we move from cathode to anode, we know that again, the charge of our electron is not changing. And we also know that the strength of our electric field is also not changing. That's just set at 50 volts per meter. In other words, we have a constant force from our electric field that's applied to our electron as it moves between our electrodes. Whenever you think of constant force and movement, you should probably think of the equation force equals mass times acceleration. So if our force is constant, and the mass of our electron is constant, which it is, then our acceleration also must be constant. Okay, so we know that our electron is experiencing constant acceleration as it moves from cathode to anode. What does that mean about its velocity? Well, we know that the velocity of a particle is equal to its acceleration times time. And our acceleration is constant, then our velocity must be increasing. And if we go back to our original equation for kinetic energy, over here, we said kinetic energy equals 1/2 m times v squared. So if our velocity is increasing, then our kinetic energy must be increasing. And that's why the answer is that the final kinetic energy of the electron will be approximately equal to the initial potential energy of the electron. So I know that was a lot of information, but that's why this is such a wonderful question, because it reviews all of these different equations that are important to understand for the MCAT. So just a quick review of what we covered. If you shine a light at a piece of metal, the free electrons in that metal are going to absorb some of the energy from those photons. And if they absorb enough to be greater than the work function of that metal, some of those electrons are going to break free and be ejected from the metal. If those electrons were at a negatively charged cathode and there's a positively charged anode close by, those electrons are going to start out with a little bit of kinetic energy left over above and beyond the work function of the metal. And then the kinetic energy is going to increase as they move towards the cathode because they're experiencing a force or constant acceleration, which means their velocity is increasing and therefore their kinetic energy is increasing. And on the other hand, they're going to start out with a lot of potential energy because potential energy is equal to charge times voltage. And initially they're experiencing that full 50 volt charge relative to the anode. But then as they get closer and closer to the anode, the electric potential they're experiencing relative to the anode is decreasing, so their potential energy also decreases. So essentially you have a flip-flop. You start out at the cathode with a lot of potential energy and little kinetic energy, and you end at the anode with a lot of kinetic energy and little potential energy. And that makes sense because of the law of conservation of energy. So if this explanation helps, please drop a like and follow my channel for more content like this.